Thank you guys for hanging around here with us this afternoon. I'll go try to be a little bit quicker to get us to get to our coffee break, because I know that I'm ready for one. If we go back, think about history. Ancient Greeks, right? They asked this really interesting question. You know, you cut something in half, you don't have two pieces, but the material is still the same, right? You cut a piece of wood in half, you still have two pieces of wood. But if you keep cutting and cutting and cutting and cutting and cutting, eventually do you no longer have a piece of wood? What can you cut to, at which point you no longer have something? And they came up with the idea of an atom, which is the smallest building block of matter that exists that you can't cut in half. So then that's where the original concept came from. What did we think was an atom? Well, way back when we had something here, they thought, well, maybe an atom was kind of like, they call it plum pudding, right? So you had little electrons, which was your plum, sitting in your pudding, which was your background of positive charge. And so this was a very popular theory in the early 1900s when Professor Ernest Rutherford sent his graduate students into the lab. And he had a alpha source, so producing heavy ions coming through and hitting the sample, and you put a detector behind your thin foil, and believe it or not, those ions, those alpha particles, go all the way through to the detector. That's great. People have been doing that for a while. Great. Plumb, they're coming right through the light parts in the atom. So then he sent his graduate student and said, haha, I'm going to have some fun with these guys. I want you to put the detector on the front side, on the same side where the source is coming from, so that you have to get some backscattering. Of course, this is really light, so nothing's going to ever backscatter. Well, this graduate student comes back and hands him the data and says, we got a lot of backscattering. So they had to go think through what's going on, and that's what gave him the idea of using a planetary model for an atom, which is what we use now, sort of. We now have quantum mechanics, of course, where you have a very heavy nucleus in the middle, and then you can have things bounce off the nucleus or go right through. And so, and I will note that this is really way too big for a nucleus, right here, this little spot. So, but it's a very heavy nucleus, so you can actually get things bouncing off the nuclei. So, Rutherford backscattering, it's an analytical technique where high energy ions, and in this case we're talking about 2 MeV, 2 million electron volts, are scattered from atomic nuclei in a sample. The energy of the backscattered ions can be measured, and this gives us information on the sample composition as a function of depth. Our first experience generally with the Van der Graaf accelerator, which is what's used in this lab for doing these type of experiments, is usually at science fairs, right? So you stick your hand on the big silver ball and your hair all stands up on end, right? And that's because we have a lot of potential there, a lot of charge. And how does that actually work? Well, you have down here something to deposit charge onto a belt, a non-conductive belt. And so the charge gets deposited now up on this ring, and it can keep building up and building up and building up until you have some way to take it out. So what we do is we put it into a helium atom, ionize the atom, and send it shooting down the tube to our sample. This is what one looks like. Whoops. This is what one looks like. We actually put it inside a big pressure vessel so we can put it up to 14 atmospheres so that we don't have the charge breaking down. And so this can actually run up to 3 MeV, at least it was designed to. But generally we do our RBS at 2 MeV. But we could also do ion implantation with noble gases anywhere from 0.7 to 2.4 MeV. In general, to use technique, we're looking at a beam size of about 1 to 3 millimeters. You know, I know with the AFMs we were just talking about, nanometers and picometers, but now we're talking about sample sizes of 1 to 3 millimeters because we have a big beam, and it needs to be flat. So So we're going to talk a little bit tomorrow, especially me, about sputtering, removing material using sputtering. This is generally done in a region with tens of kilovolts down to 1 kilovolt, even a little less. And so in that case, you're actually having the electron clouds of the atoms and the ions that you're working with bouncing off each other. So you can think of these as quite big. Did it again. So you can think of it as quite big and dense. Everything is, all the spaces are filled. But when we're working in the MeV range, here, then we're only really talking about the nuclei, and so therefore you can really think of it as very, very undense. So lots and lots of space. And so you can actually think of your whole sample as just looking at all the atoms as if they were on a plane. And so when you're doing that, you have to be a little, you can talk about atoms per square centimeter instead of atoms per cubic centimeter. Now, of course, we can't completely discount the electrons when we're doing our work, because they can actually act as like a dragging force on the ions as they go through the solid. So our helium ions are going through, and we have two major effects. One is, like I was talking about, that drag effect, and the other is billiard ball collisions. So if you do pool, you know, you smack the two balls against each other, one of them scatters off, one of them moves on and recoils, and so that's exactly what we're talking about here. We have an incident ion comes in, hits target material, and gets scattered, and then you have recoil for mass 2, freshman year physics, conservation of energy, conservation of momentum. Great, we can do this problem. You've got a nice equation down here talking about the energy conservation, and it has a kinematic factor here, function of masses and angles. Great. So what does this, when we plot that out, what do we get? Well, what can we learn? First, helium will backscatter from anything greater than mass 4. Okay, that's great. I'll backscatter from anything we're really interested in looking at, except for hydrogen. But that's pretty good. Second thing, from the shape of this curve, we can know two things. One, we get pretty much a lot of signal back from things that have a high target mass. And so therefore we have a lot of sensitivity, so we can measure low concentrations. Down here we don't have as good a sensitivity, but what we do have is we have good selectivity. And so that means it's a lot easier to tell what you're looking at, because the peaks tend to get separated further. So just what's nice about this also is because we have a Coulombic interaction between the nuclei, we can actually determine an exact expression for the backscattering. Thus we can say that RBS is a quantitative method. It's a fully quantitative method. And we can define a scattering cross-section, that's this right here, as a function of energy and angle, which ends up being proportional to the atomic number divided by the energy quantity squared. So, conceptually, what happens during an RBS experiment? So I'm going to come up with a hypothetical platinum silicon alloy. And so what happens? So we have some situation where we're coming in and we're bouncing off the surface. So we have two options. We can either bounce off of platinum or we can bounce off of silicon. If we bounce off of platinum, we'll come in on our energy scale. It'll drop a little the energy for bouncing off the platinum and come back out. And so we'll have some energy here. It could also go through the sample to the back surface, bounce off, and come back. Well, like I said, we have some electrons dragging, so we're going to lose a little bit of energy as we're traveling to the back surface. We're going to scatter down. You'll see this amount of scatter is the same as this amount of scatter. And then we're going to lose some energy coming back to the front. And so then, as a function of thickness, we're going to have an energy distribution. So there's going to be a change in energy. So we can use that to figure out how thick our sample is. Now instead, we come in and we bounce off of a silicon atom at the surface. So we're going to go down a much further distance. We're going to lose more energy. And so and then of course we have the same effect if we go to the back. So we're going to end up having a second band talking about the silicon. So we can actually calculate those out and do results from that. Another hypothetical alloy, in this case we're talking 20% gold, indium, titanium, aluminum, and oxygen. Reason why these were picked is, and it's on a carbon substrate, reason why these were picked is we're kind of doubling-ish the atomic number as we go through each of these. So I'll remind you of our shape here. So what do we got? So we have 10 monolayers of our film, and we can see we have a lot of counts for gold, less for indium, less for titanium, aluminum, and oxygen. So we can see we have much higher sensitivity for the higher Z materials. Also, you'll note that the indium and the gold are kind of closer together than the aluminum and oxygen, but the difference in the Z number for aluminum and oxygen is 7, and from indium to gold it's like 30. And the indium and gold are closer together, so that tells you we have a lot less ability to select, to know what we're looking at. So, for 10 monolayers, we have about 12,000 counts full scale, and we have these things. As we go up to 100 monolayers, so we've increased it by a factor of 100, a factor of 10, we have many more counts. The substrate is becoming harder to see, but we have still a lot of counts from our other things. If we keep going thicker, now all of a sudden we can see here in the aluminum, titanium, and oxygen, we actually have a flat top on our peaks. And that's information on the thickness. So we've got scattering from different points all throughout our film. And the indium and gold were close enough together that they're now starting to overlap. And so you can just think of this as a sum of, in that one region, of the indium plus the gold for the counts. So it's just a simple sum. As you go thicker and thicker to 4,000, you have more and more things that are starting to overlap. And eventually when you get really, really thick, then everything kind of just mushes together and you no longer have that sensitivity. This is a calibration sample, so if you're actually trying to do a measurement, it's useful to run a calibration sample first to assist in setting up the instrument parameters. So this sample is a gold thin film on top of a copper thin film on top of silicon. And so that's what we remark about in these areas here. But for the calibration information, we have information on the geometry. So basically how this beam, the sample, and detection angles that we use. And also we have information here on the calibration offset, energy per channel, and particles tied in steradians. That's where the calibration really comes in and useful, because it allows you to get a first handle on the calibration offset energy per channel. So basically, how do we calibrate our x-axis? And then the particles per steradian helps calibrate our y-axis, although that one changes based on how long you're taking your measurement for. If you can see here, you can see that we are talking about thicknesses in terms of atoms per square centimeter. So of course you have to know the density of your sample, atomic density of your sample, if you want to be able to convert that into an actual atoms per cubic centimeter. This is another sample that was done. It's actually a copper niobium tungsten alloy. So it's an alloy, so it's one layer. And so when you see the copper, the width of the copper peak is going to be the same width as the niobium and the same width as the tungsten. But they come up, the tungsten being the heaviest, comes up first, then the niobium, then the copper. They all exist at the surface, so they all start at the same time. They all start at the front surface, whereas the silicon is deeper, and so it's going to start not at the surface, and so you can find that out. The copper, niobium, and tungstens are thick. That layer is thick, so they do overlap. And one of the neat things is tungsten, being a high Z material, does have a very low concentration, less than 1%, but it's still visible. Another example showing some of the similar things. This program that we're using here is called SimNRA. There's two main programs that people use. They use this and a program called RUMP. Both have different advantages. What's nice about this is, like I said, to do this analysis, you have to have information on the cross-section of all your different elements. But since these are known and don't change, you can write a computer program to do all the hard work for you. As a matter of fact, this software will even fit your data. Obviously, there's still a lot of human involvement with it, but if you're close, it'll get you there. So usually people know either they know what materials they have kind of close, they're not sure about their thickness, or vice versa. They'll know their thickness is pretty close, but they're not quite sure about their composition. And so you can definitely get it from there. Some highlights here. You can see that we have 1.8% zirconium. We can still see that. And this nitrogen level here, so if you take that across, the nitrogen is 50%. So therefore, much lower Z. And so you have to have a ton of it in order to be able to see it well. We do have thickness effects that can occur in RBS, so it's something to be wary of. So we have a titanium nitride on MgO film here. And so you can see we have the titanium signal here. So here's titanium at the surface, here's titanium at the interface, here's nitrogen at the surface, and our substrate is MgO, so this is a buried layer. So here's the magnesium. If you get at the right thickness, you can actually be in a situation where the nitrogen from the surface and the magnesium from the interface are at the same energy, and so it causes some questions, you're not sure about it. Of course, if you grow thicker, then the nitrogen at the surface doesn't move, but the substrate moves, and so the magnesium moves further in, and so now you don't have that problem anymore. If that is an issue for you, you can actually choose to use a different set of angles. And then, for instance, here's our 400 again. If you move to a different set of angles, then you can pull the nitrogen away from the magnesium peak. This second one, we tend to call it more surface sensitive. You spend more time with the ions going through your film because you're at a higher angle, higher incident angle. A couple of quick examples here. This is a titanium aluminitride, titanium niobium nitride, multi-layer film with 2 nanometer periods. Not able to resolve that in RBS, but you can get average information. And so, of course, we have information from the niobium, from the titanium, the aluminum, and the nitrogen. Again, nitrogen being 50%, but it doesn't show very well because it's a much lower Z material. And this was an example of oxidation experiment done with titanium nitride on SiO2. So this is, this is your sample with the titanium peak here, and you have some nitrogen peak here. And then when you oxidize, you actually drop the level of the titanium peak from 1 by 1/6. Then that's because you're going from TiN, where it's 50%, to TiO2, where it's 33%. And then you also pick up an oxygen peak here. From this, of course, we can then get the thickness of how far into the titanium nitride you've actually oxidized. So to summarize, RBS is a quantitative technique for elemental composition. Does require flat samples, and the beam size is large, 1 to 3 millimeters, but it can be non-destructive. For polymer type layers, you will burn your layer, but for metals and semiconductors, it's basically non-destructive. The detection limit does vary from 10% down to 10 to the minus 6, but that's very dependent on the atomic number, and it's optimal. The best type of experiments is when you have heavy elements on light elements. So for your substrates, you generally want something like graphite or silicon, and then you're looking at heavier metals. And then we can also get depth information from monolayers up to a micron. I'd like to thank our sponsors again, because without them, then it makes it much, much harder to be able to do this work. And I enjoyed the talks that we had earlier today. Thank you.
We actually have time for a few questions if anyone has any, or if Oklahoma State does. So, front row.
So, what kind of limitations do you have on thickness of the sample? Does it have to be very, very thin, or do you have a thick sample that will interact with the first micron?
So you will only act with the,
Yes, could you please repeat the question first?
he asked what kind of effects can you have with thickness? Can you look at very, very thick samples? And the answer is you are limited to like a micron or two in total thickness, at which point you stop seeing things as the depth. So therefore, you will see the top layers, but you won't get any real signal from the layers behind it.
So in that case, your like layer thickness information will just be the penetration.
Yes, the penetration depth. Yep.
And then just one quick question that I had is that given that you lose some energy due to the electron cloud within the material, does that ever change based off of the kind of alloy in terms of chemical environment?
You would think it does, but it doesn't seem to have a big effect. In the RUMP program, one advantage that it has is there is an effect as you go deeper and deeper dependent on the material, but it's small. So generally most people don't worry about it.